implies the existence of pseudorandom generators. Okay, so pseudorandom generators is really a minimal assumption in cryptography. We can ask whether it is useful in cryptography, and there are a lot of interesting notions in cryptography that are implied by the existence of pseudorandom generators. And so, for example, you can base private key encryption, digital signatures, bit commitments, and so on, just on the existence of pseudorandom generators. And of course, you can also combine pseudorandom generators with other assumptions to get even more primitives. So the bottom line is pseudorandom generators are very useful in cryptography. It's also useful in other areas in theoretical computer science. It shows up in algorithms. So we know that if you have really good pseudorandom generators, then you can show BPP equals P, for example. It also comes up in complexity theory, learning theory, and so on. Okay, this was about pseudorandom generators. What about pseudorandom quantum states? And even pseudorandom quantum states are like very useful in quantum information. So for example, pseudorandom quantum states was used to show connection between wormholes and ADS CFT correspondence. It was also used to show some space complexity lower bounds in quantum machine learning. It's also useful in quantum complexity theory. Again, the Kreshmer's result was mentioned in the previous talk. Okay, so this is about pseudorandom generators and quantum states. So we can take a step back and look at the bigger picture. So pseudorandom states belong to the this world of quantum cryptography, and pseudorandom generators belong to the world of classical cryptography. So in quantum cryptography, you allow the algorithms to run in quantum polynomial time. You allow for quantum communication and so on. On the other hand, you have classical cryptography where you restrict the algorithms to run in probabilistic polynomial time. The communication is classical and so on. So how do we compare these two worlds? Right. So I should mention that there are a lot of works especially showing that these different primitives belong to this world. Some of it was mentioned in the previous talk. You'll hear more about them in other talks today. Okay, so how do we compare these two worlds? On one hand, quantum cryptography could potentially require weaker assumptions than classical cryptography. Right? So there's some evidence to believe that that is the case. On the other hand, quantum cryptography inherently requires quantum communication, and in many places that's an issue. Right? Like for example, even if quantum computers do come into existence tomorrow, you really need quantum networks also to be in place in order for these applications to be implemented. There are also other places where quantum communication creates an issue. For example, if you're looking at public key primitives, and if let's say your public keys are associated with quantum states, right? So now there's a problem with distribution. So do you publish many copies of this state online, or like do you distribute to each user on a user basis? So these things need to be taken into account when you have quantum communication. Okay. So now the question is, can we get the best of both worlds? So can you get a world where this world could use weaker assumptions than classical cryptography? Or on the other hand, it just relies upon classical communication. Okay. So this is sort of the direction that we are interested in. And indeed, you can consider this world called as hybrid cryptography, where you allow the algorithms to run in quantum polynomial time, as in quantum cryptography, but you enforce that the communication has to be classical. Right? So, and there are many primitives that come into this class that I've studied previously. This is not something new. So what do we know about hybrid cryptography? The advantages are obvious, like again, you just need classical communication, just like classical cryptography. On the other hand, there is a possibility of basing it on weaker assumptions than quantum cryptography. So what I'm going to focus on is I'm going to look at one primitive in this class of hybrid cryptography that we call it quantum pseudorandom generator. And we're going to look at the relationship between quantum pseudorandom generator and pseudorandom states, and also quantum pseudorandom generator and classical pseudorandom generators. Okay. Okay, so what is a quantum pseudorandom generator? If you're familiar with pseudorandom generators, just replace PPT with QPT, and you'll pretty much get the definition. So in more detail, quantum pseudorandom generator has a function associated with it. So it maps n bits to m bits, and it's important that m should be larger than n. And just like a classical pseudorandom generator, we require that there is an efficient algorithm that implements F. And in this case, we allow the algorithm to be QPT. So since the algorithm here is quantum, we have to explicitly enforce the determinism requirement, right? So we want the algorithm to be almost deterministic. So if you run it on the same key twice, then the probability that you get the same output should be very close to 1. So here we allow like inverse polynomial error. Ideally, we want this to be negligible. But in this talk, I'm going to consider this to be inverse polynomial. Okay, security is as the same as pseudorandom generators. We require that any QPT algorithm cannot distinguish whether I get the output of a pseudorandom generator or I get a uniformly random string. Yeah.
Is that definition like conditioned on outputting correctly? Like, is that indistinguishable FK from UM or GK?
No, it's just always the case.
I see. So even if like your G outputs a bad string with some inverse poly probability, you still want it to look uniform?
Yes. Okay. Here, I'm only giving one sample. Like if I give 2 samples, then it's trivially distinguishable. Yeah.
Right. Okay.
Yeah. Any other questions? Because with inverse polynomial probability, they might not be the same. And here, I'm going to get the same copy twice, right?
So you have actually 2 security requirements. One that F is indistinguishable from random and one that G is indistinguishable from random, because neither implies the other.
No, this is the only security requirement we have.
So F might be distinguishable from random.
I don't care about whether F is distinguishable from random or not. All I care about is D implements F.
Probably not, right? Because there's so much overlap between G and F.
Yeah, because it implements G approximates F with very good probability, right?
It's certainly stronger that G is indistinguishable from random, though.
Is this for random K or for every K, the pseudo-determinism?
Random K, just like
yeah. Then there could be a big bunch of Ks for which F and G are different, and F happens to be 0 on all of those. So let's say G. G is an actual PRG, just a classical PRG, and F is equal to G, but on a inverse polynomial subset of the values fixed to 0.
But it depends on what is second F. Sorry, did you just ask this? Or
yeah.
The second one is for all K?
Which one? Just definition?
Yeah.
So this definition, again, the probability is over K and the randomness of G.
Okay, so then I agree with you.
Yeah, so it's mutually the 2 things don't imply each other.
Yeah, so I don't care about the indistinguishability of F. Okay. I care about this indistinguishability of G from the reason I specify F is, I need to say what does it mean for it to be a deterministic output, and F actually specifies what it means to be. Okay. Any other questions? Okay, so we're going to look at the relationship between quantum pseudorandom generators and PRS and PRGs. So our first positive result states that any pseudorandom state with logarithmic output implies the existence of quantum pseudorandom generators. Okay. I'm going to dive into the results a bit more. So this is sort of the informal statements. And secondly, we show that quantum pseudorandom generators can be as useful as classical pseudorandom generators in many applications. So for example, just like you can use classical PRGs to construct commitments, encryption, and so on, you can also use quantum PRGs to get these applications. Okay, so let's look at the first result in a bit more detail. So what we show is that if you have PRS generators with seed length n, and the output length is some constant times log n, you should think of this constant to be something like, it should be at least 10 for now. Then such a PRS implies existence of quantum pseudorandom generator. Of course, n to the C prime should be larger than n. And in some sense tied because if C is a very small constant, then you can even get this information theoretically. So you need C to be a large enough constant to show that this implies existence of quantum PRGs.
Prabhanjan, does your pseudo-determinism definition make it not possible to have indefinite length extension? Like where you get stuck after getting some fixed polynomial stretch at some points, you won't get pseudo-determinism anymore?
Right. So all these classical transformations don't immediately work for quantum PRGs. Yeah.
Are these two just equivalent though? Like if you have a quantumly computable string, can you just turn it into a pseudo-random state?
The pseudo-randomnism is an issue. because if you do the JLS construction, you're going to get a mixed state.
I see, but it's like you get a particular pure state with like pretty good probability, right?
No, it's one out poly away from any pure state. And even there's another issue, which is that for JLS construction, you need a PRF and not a PRG. And you can't do the GGM transformation. That also is not going to work if you go from quantum PRG.
I mean, you just need a long random string, like much longer than your state, right?
So if you're just using like log.
I'm asking, does QPRG imply a log length output?
Okay, if you're just interested in log, yeah, that's the issue I mentioned. Like it's going to be inverse polynomial away from any pure state.
Interesting. Okay.
Okay, any other questions? Okay, at this point, you might be wondering, there is actually a separation from PRS and PRGs, right? Why doesn't this contradict that separation? So it turns out that if you like look into Kretschmer's proof, it turns out that the separation only holds between super logarithmic output PRS and PRGs. So we are not violating any separation. Okay. Okay, so in terms of cryptographic applications, as I said, we get all the applications or many of the applications that are implied by the existence of classical PRGs. The one advantage we have in our work compared to the other crypto applications in the previous papers is that our constructions are conceptually much simpler than the previous constructions in the sense that they resemble the textbook constructions of these primitives. So if you open any Crypto 101 textbook, if you look at the constructions of commitments and one-time encryption, our constructions resemble those constructions. And another advantage is that our applications only use purely classical communication. Okay. So how do we interpret our results, right? So there are two possibilities. So one possibility is that quantum PRG is really a weaker assumption than classical PRG, or it could even be incomparable. So in either of the two cases, it's a win for us because we can get all these interesting applications from assumptions that are qualitatively different from pseudorandom generators. But there's another possibility. Maybe quantum PRG and classical PRGs are really the same. We haven't figured out how to prove it, but maybe they're the same. So in that case, our result gives an interesting conceptual message. So since PRG is separated from super logarithmic output PRS, and quantum PRGs can be obtained from logarithmic output PRS, there is a separation between logarithmic output PRS and super logarithmic output PRS. So it says that you might potentially need stronger assumptions to get logarithmic output PRS than super logarithmic output PRS. To me, this was very surprising, because in classical pseudorandom generators, getting fewer pseudorandom bits is easier. Just throw away whatever extra pseudorandom bits you have. But here it says that if you want to get small amount of pseudorandom quantum bits, you probably need stronger assumptions. Right? And it also says that if I give you a PRS and if you want to generically shrink the output of PRS to get something small, this could be hard as well. So in either of the two possibilities, we believe that our work has some interesting consequences. Any questions? Okay, so we also show how to come up with, yeah.
Sorry, these acronyms always throw me off.
Sorry.
So PRS is a pseudorandom state.
Yes.
Okay, so you're saying if you're given a pseudorandom state on n bits,
yes.
You ask, are the first n over 2 bits pseudorandom state? It's not clear.
It's not. I mean, if you just throw away, you're going to get a mixed state. And you can show that if it is very mixed, then it's going to be distinguishable from many copies of our state.
I think the crucial fact is that the pseudorandom state generator has to output pure states by definition.
Pseudorandom states, yes, almost pure. It's need not be the case that it always outputs a pure state. As long as it's close to some pure state, it's good enough.
The PRS, I thought by definition it has a pure state.
No,
but in any case, if it's close to pure state, then chopping off something would not satisfy the definition.
Okay. So in that trivial sense, it's not, but there wouldn't be distinguishability. It's just that it's no longer pure.
No, it will be distinguishable. So suppose let's say I give you 2 copies of such a PR state, then they will be distinguishable from two copies of the same hard pure state, right? We'll just do like a swap test.
Oh, I
check.
see. Okay,
So, but because of that, any PRS state has to be almost pure. Yeah.
So doesn't it seem like there's a difference in how you define a QPRG versus how a PRS is defined, where like for a PRS you need for all k that like psi k is like deterministic or like almost deterministic.
Yeah.
And here your requirement is like for a random k that you're kind of right. But why wouldn't you define it? You alternatively define it to be that for all k you're almost deterministic.
So these two are different primitives, right? Like one PRG is something we define in the paper.
Right.
You can potentially require this. We consider like a weaker requirement that is sufficient for applications, and we can also build it from logarithmic-output PRS. But you're absolutely right. We can consider the stronger notion.
Yeah, I feel like the other one would probably be equivalent to PRSs,
Probably, that's true.
like log length.
Oh, I don't say it's equal. Again, one direction I can see to go to PRS. I don't know how to go from PRS to this kind of a QPRG. Just because of the continuous nature, like there will always be some inverse polynomial error. You will see when we talk about the techniques, you will get some more intuition as to why we can't get it. Okay. Any other questions? Okay. Yeah. So we also consider quantum. Yeah.
sorry. So if you go back again, sorry. Now I'm really curious. So you're saying, well, yes. So they are distinguishable because now these are not pure states anymore.
Yeah.
But now you're saying, well, it really has a consequence, and is the consequence of the same nature or is it of a different nature? Now I don't understand this this possibility too. So can you put some can you sort of say, so all this is in the abstract, so can you sketch out what it is that?
What are these consequences?
Yeah, because now I don't understand where it's coming from, right? So
right. So we want to understand how different is logarithmic output PRS from super logarithmic output PRS, right? Is it that they the same assumption or are they separated or not?
No, I understand that it may not be the same assumption,
right.
In the sense that in the sense that there's this pure state, mixed state issue. But now are you saying that because of this, we might think, okay, well, this pure state, mixed state issue is a technicality, sort of. It's how we defined it, but you're actually saying no, it has a consequence.
Yes.
For something else. Now, is that consequence of the same nature or different natures? Are you saying no, but these are actually stronger objects than you would imagine because you can do this kind of cryptography? It's not just different because of the change in
right. So the consequence is that here the consequence is more of like a conceptual message rather than getting some concrete cryptographic applications. Mm-hmm. The conceptual message is just that you might need stronger assumptions, stronger computational assumptions to get smaller amount of pseudorandom qubits versus large number of pseudorandom qubits. To me, this is like surprising because classically, getting small amount of pseudorandomness is easier. In some cases, it's even strictly easier than getting a more amount of pseudorandomness. So there's no like applications per se here. It's just about understanding how like logarithmic and super logarithmic output PRS. Okay, so let's move on. Okay, so we also get quantum pseudorandom functions, and we have some similar applications for quantum pseudorandom functions as well. Okay, so let me jump right into the techniques. So it turns out that to show the positive result, which is what I'm going to be focusing on, I want to talk about the crypto applications. So to get the positive result, it turns out that our main tool is to get an extractor, where the extractor gets as input many copies of a state psi, okay? And it outputs a binary string. So what are the two requirements on this extractor? So one requirement is that you want this to be generated pseudo-deterministically. What this means is that if you run the extractor again on t fresh copies of the state psi, then you should more or less get the same string. That's the first requirement. The second requirement says that if psi is a Haar-random state, then y psi should be distributed according to the uniform distribution. Okay, so these are the two requirements, and we'll see how to achieve it. So let's start with a thought experiment. So we'll come up with an extractor that's not physically implementable, but it helps to think about it. So we're going to look at a deterministic ideal extractor that has two properties. So the first property is the determinism requirement that says that if the extractor is given amplitudes of a Haar-random state, okay, then it outputs f of psi, where f of psi is f is a continuous function that maps all the points in the unit sphere to binary strings. So you can think of like partitioning the unit sphere into many regions, and each region is associated with a binary string. Right? And we want that the probability that it outputs f of psi should be very close to 1. In terms of security requirement, we just want that the output distribution of the extractor should be close to the uniform distribution. Okay. Okay, so how do we come up with this extractor? So the initial hope would be that maybe from every amplitude I can extract some bits of randomness, but that's just not possible because all the amplitudes are correlated with each other, right? You want the sum of squares of amplitudes to 1, right? So you can't hope to extract from all of them. But what if we discard some of the amplitudes? So then maybe I can still like extract some uniform randomness from the rest. Right? So and that's what we're going to do. So we're going to use a fact about uniform spherical measure, which says the following. So if you, yeah.
That you're given amplitudes.
Yes. For now, I'm going to do that. Later on, we'll try to come up with a physical like extractor. Yeah. Okay, so I'm going to, what this fact says is the following. So if you pick a random point on the unit sphere, and if you throw away some coordinates, then they're going to be close to the Gaussian distribution, okay, IID Gaussian distribution, where the mean is 0 and the variance is like, standard deviation is going to be 1 over d. Okay. And how many coordinates are we throwing on? I mean, so let's say we are only considering k coordinates, then the total variation distance between the first k coordinates and k IID Gaussians is going to look like this. So all you need to remember is that we're going to work in the polynomial dimension space, which means that d is going to be some polynomial. Okay. So note that we are going to apply this for logarithmic output PRS, which means that we are working in like polynomial dimension Hilbert space. And then we should think of k to be something sublinear in d. So if you substitute the parameters, you're going to get the total variation distance to be inverse polynomial. That's all you need to remember right now. Okay. So what are we going to do? So we have these different amplitudes given to us. So we're going to discard some number of them towards the end. And we know that like each of them is close to Gaussian distribution. Okay. So this gives a natural rounding mechanism. So what I'm going to do is, if this amplitude, I'm going to look at the real components. Yeah.
Right, it's got a little bit lost. Can you just, are the alphas, they're supposed to be the Gaussian, like complex Gaussian coefficients of a Haar-random state?
They are the amplitudes of a Haar-random state.
I see. And your problem is that you want to deterministically turn this into a random classical string.
Yes.
Like supposing that you have a mechanism for learning all of these amplitudes.
Yes.
You want to turn them in, and you're saying you can't just output the amplitudes because they're normalized and so they're actually not like uniform.
Yes, exactly.
I see.
Exactly.
Okay. All right. Thanks.
So I'm going to look at the real components, right? And each of the real components are going to be close to the IID Gaussian. So then this gives rise to a natural rounding mechanism. So what I'll do is that if this is above 0, then I'm going to extract the bit 0. Okay. If it is below 0, if the real component is below 0, then I'm going to extract the bit to be 1. Okay. This is how I'm going to extract the bits from all the amplitudes. So just to do a very simple exercise, so if I have like 4 amplitudes here, so I'm going to look at the real components. So the real component here is 0. So then the first case, you have the value to be larger than 0, so you're going to extract the bit to be 0. Second case, it's 1. Third case, it's 0 because the real part is 0, and fourth case, it's 0. Right? So you're going to output 0, 1, 0, 0. Okay. Okay. Of course, this was a thought experiment. It worked great, but it was a thought experiment. You can't really hope to get all the amplitudes in the clear. So that's the first issue. It's like, how do you come up with a physical implementation of this extractor? And the second issue is that there's still like 1 over 2 to the n total variation distance from the uniform distribution. And you might think that this is not that much, right? Like, I mean, this is negligible in n. But note that we are working in the setting where n is something logarithmic. So you're going to get the total variation distance to be inverse polynomial with uniform. Yeah.
If all I'm doing is taking the signs of the random state, why do I need to throw out some of the entries?
Yeah, because they're correlated with each other. You have to argue that they're going to be uniform.
But you actually can't learn all the signs, right? Well, let's say you could learn the signs.
You,
I mean, aren't the
you can learn
signs
the parodies of the signs. Like, you can
The
learn the
science
parodies
is
of
how
2 and
I'm
7
extracting
signs.
all the bits. Yes.
But aren't the signs uncorrelated with each other?
Okay, if that is true, then you can do that. You don't even have to throw it. So we were relying on this result, or this is how we were able to argue that they're uncorrelated. Yeah, happy to talk about it.
But aren't the signs kind of physically I mean, the thing
Consecutive
is,
signs. Like,
sorry?
look at the parity between 0 and 1, and then 1 and 2, and 2 and 3. And those are going to be independent binary, like plus minus ones.
I have problems as soon as complex numbers come into this picture because it's all up to global phase. So is it kind of like we ask whether
None of this is physical, right? I'm going to come up with another implementation where we'll take all these things into account.
Yeah, sure, it's not physical, but I mean, kind of, it's even less physical if we are talking about the actual, like,
Yes.
There's one problem, given
Yes.
a quantum state, I can't figure out
Yes.
those alphas, but there's the additional problem that given a state that is actually, I mean, they aren't really pure states, they're pure state modular global phase,
Yes.
and then these values are not even mathematically well defined. That's my problem.
Right. So right now, just think of them as me giving many complex numbers drawn from some distribution. Yeah.
So it sounds like you're going to give us an even better solution.
I wouldn't say even better. Something that is implementable.
Okay.
Yeah.
So better.
Okay. Okay. So there are two issues, as I just pointed out. So the second issue, let's just ignore it. We can extend some known classical security amplification techniques to deal with this. So let's just focus all our attention on the first one. How much time do I have? Continue. Sorry. Okay. Let me try to increase the pace. Okay. So let's come to something that's more physical. So in this case, like, I'm not going to give you the amplitudes in the clear, of course. So what I'm going to give you is many copies of a Haar state, right? Again, it's exponential in n number of copies of the Haar state. And then the goal is still the same as before. I want to output some string that is sort of pseudo-deterministic with very high probability. Okay. And I don't want this to hold for all the states I. I just want this guarantee to hold for state psi that belongs to a good set. I'm going to argue that if a state is a Haar-random state, if you sample the state from the Haar-random distribution, then with very good probability, it's going to belong to the good set. So condition on the state being in the good set, the extractor is going to be pseudo-deterministic with a very high probability. Okay, so we don't have this like very nice picture earlier where like we divide into different regions. There are some gray parts where we have no guarantees whatsoever. But in the other regions, we can sort of extract the string with very high probability. Okay, so there are two steps in the description of the extractors. The first is to perform tomography. Second is the surrounding procedure. So the first step is more standard. So if I give you enough number of copies, you can sort of recover a classical description of the state. So you have the state that is like close to the density matrix associated with the Haar-random state psi. So since they are going to be close to each other, so I'm going to work with this. Even though I don't get this in the execution of the extractor, for the analysis, I'm going to work with this. Okay, so once you get the output from the tomography procedure, the next step is to do some rounding, right, to extract the uniform bits out of it. So all I care about are the diagonal entries. The other entries are not important to me. Okay? So what I'm going to do is I'm going to throw away some columns. Okay? And the diagonal entries I'm going to divide into different blocks. Okay? And then I'm going to sum up all the entries in each block. So I can show that each of these entries is as if we were sampling from a chi-square distribution. So if you sum up all of them, we can use central limit theorem to show that they're going to be close to the normal distribution. Okay? So you can do that for every coordinate. Every block. Okay. Right. So you can consider the first block, sum up all the entries in that block to get Q1. Consider the second block, sum up all the entries in that block to get Q2, and so on. And all these different QIs are close to IID Gaussians. So the mean is not going to be 0 anymore. It's going to be shifted, but that's not a problem. Okay, so what is going to be the rounding procedure? Just to summarize, so you're going to discard some columns, and then you're going to break the diagonal entries into different blocks, and then sum up all the entries in each block. Okay? And then you're going to do the rounding procedure. So since they are close to IID Gaussians, so you're going to, for each coordinate, you're going to round depending on whether it's higher than the mean or lower than the mean. Okay, so this is going to be the mean. So if it is higher than the mean, you're going to classify it to be 0. If it is lower than the mean, you're going to classify it to be 1. Okay, so this is all like assuming that we had this actual matrix psi. But of course, you don't have the access to that. You have whatever you get out of the tomography procedure. Right, so if you work with this, even though they're close to each other, there might be an issue, right? Because there's an error that results in the tomography procedure. And how does the error affect us? So if the QI values were very close to the mean, even if one of the QI values was very close to the mean, then the tomography error could be so large that every single time you run, you're going to get 0 and 1 with maybe the same probability. And that's bad, right? So you really want the QI values to be very farther away from mean as possible. So that's how I'm going to define the notion of good states, right? So the sort of good states are going to be, I'm going to call a state of states to be good if all the QI values are far from the mean. So that the tomography procedure, whatever error that results in the tomography procedure, doesn't cause a classification error. And then you can show that with high probability, any Haar-random state is going to belong to this set. It's not something I'm going to talk about, but you can sort of show this. Okay, so all this discussion was about coming up with an extractor. How is this useful to go from a logarithmic output PRS to quantum PRGs? So here's what I'm going to do. I'm going to run the PRS many times to get many copies of the PRS state. And then I'm going to run the extractor on many copies of the state to get y psi. And then I'm going to output y psi. Okay. Okay. Yeah.
Like one of our poly-variational distance solved by using this chi-square thing.
That's still an issue. So that's why you only get 1 over poly-determinism error.
Okay.
It also causes an issue in security, but there we do some security amplification techniques to get negligible error. But for correctness, we don't know how to get rid of it.
If we would get rid of that part, I mean this distance from uniform in the sampling, would that help us? Because we still have the tomography error, which makes it pseudo-deterministic. So would we get any advantage if we solve this problem? So if we manage
that is true. That is true.
Yeah, because I think you could do it by just adding an extra seed and using classical randomness extractor based on that. So I think this sounds like the solvable part of it, but I'm not sure.
No, that also I'm not sure. Like I think the fact that we used there 1 over poly is like the best you can do. But you're right. Even if you have somehow you can come up with another argument to solve that issue, tomography is going to be it. Thanks. Okay, so that's how we get a quantum PRG, and then you can show that the output distribution is computational distribution from uniform by relying upon the security of PRS. Okay, Okay, so this concludes the, so the high-level description of getting quantum PRG. So let me sort of give you some open questions to think about. So I divide this intermediate area that is sandwiched between quantum cryptography and classical cryptography, and our work sort of explores the connections between PRS and classical PRGs via this primitive. So one interesting question that we still don't know how to solve is classical PRGs and quantum PRGs that different? Can you show a separation between both of them? That's something that we don't know how to do. Or maybe there is no separation, right? In which case, can you show that like logarithmic output PRS and super logarithmic output PRS are separated from each other? So either of the two questions should be true. Can you solve any of them? Sorry. And then another thing is that this there's an inverse polynomial error. Can you reduce the error to be negligible, right? Like so somehow if you come up with another argument, as Fermi was mentioning, you can then show that such a notion of quantum PRGs and logarithmic output PRS are going to be equivalent to each other. This is another open question. Either prove an impossibility or a positive result. And finally, we show that this is related to the previous question. We show that logarithmic output PRS implies quantum PRGs, but you can somehow show that quantum PRGs implies logarithmic output PRS. We still don't know how to solve this problem as well. So with that, I conclude.
If you can construct PRA, quantum evaluation PRA.
No, there are two problems with this. One is that I don't know how to go from quantum PRG to quantum PRF directly. First of all, like if you try to define quantum PRF, that itself is going to be non-trivial. So somehow, let's say you manage to do that. I don't know how to go from quantum PRG to quantum PRF. And the classical GGM transformation does not work. That's the first problem. Second problem is you have to still solve the inverse polynomial Pseudorandom error. Because even if you got quantum PRF with the inverse polynomial error, I don't know how to get PRS from that.
But maybe if you can solve that, you can construct general PRG log out of the out PRG. Just so you can.
Yeah, that's actually possible. That's true. That's true. That's true. Yeah, that's a good point. Yeah.
So there's something that kind of confuses me. So in classical complexity theory, there's this theorem, this Stockmyer theorem, which is about counting the number of solutions. And the way it sort of works is you say, well, if you could count and you can apply some random hash of the solutions, then you can approximate the count by just seeing, does there exist something which is a solution and simultaneously the hash. So if you have this map that takes the Haar measure and it extracts out these classical values, doesn't it imply something very strong for this quantum approximate counting thing? I thought those were not known to exist.
Like what is the consequence?
Well, basically, it's like the Hilbert space. There's no way of like halving it easily.
Right. So here, I don't know whether the determinism error is related to your question. Like we don't know how to actually divide the region exactly in such a way that you can designate regions to each string. There's always boundaries where you're going to mess up. I don't know whether that is going to cause a problem in extending the results that you're talking about in the quantum setting. We can talk more offline. Yeah.
So two minor things. So your first answer to Tomiyuki's question, Zvika and Omeo's paper on asymptotically random states where they show a random function, you can basically create a Haar-random state of very short output length.
Yes.
And I feel like that should only require a polynomial number of random bits to instantiate when your qubit length is very small.
I think his question was different. So he's asking whether you can go from logarithmic output PRS to, let's say, super logarithmic output PRS generically.
Oh, okay. Sorry, I thought you were asking whether you can go from quantum PRG to log output PRS.
Yes, we are.
Oh, okay. Then never mind. Totally.
But this is just also an interesting generic transfer. Yeah.
Yeah. But okay. The other thing I was wondering is like you're talking about sort of assumptions weaker than one-way functions. But I guess, you know, there's a lot of things that are potentially weaker than one-way functions. Yes. And it feels like maybe on that sliding scale of like how weak things are, this is like pretty close to one-way functions, right? And that like, if BQP equals QMA, these don't exist, but then there's still all this other stuff that does.
Honestly, I don't know. I don't know whether it is really close to, that's why I raised the two possibilities in the talk. Either way, I think this is just saying something interesting. Like if we can show that it is close to one-way functions, that would be amazing.
Right, I guess close in the sense that there are complexity theoretic like collapses that would actually rule these out.
Right.
Whereas those same collapses wouldn't rule out like E and I, right?
But that doesn't necessarily mean that it is closer in terms of like computational assumptions compared to classical crypto, right?
Sure.
It just says that like some
Right,
of the
right,
techniques don't. Yeah. But yeah, you're right. I mean, it's really very interesting to understand. Yeah.
So this implies a pseudo-deterministic one-way function, doesn't it?
Yes. So QPRG is a quantum one-way function, if you can define it appropriately. But, yeah. Any other questions?
Can you construct universal one-way function? So that is really you can construct many times secure sequence.
No, I think the problem is that we thought about signatures. So the problem is that the pseudorandomness is not a cause and error. Like whenever you run the same thing twice, you might be able to sort of distinguish whether you're in this world or the other one. This issue doesn't occur for PRG because I'm always going to give you only one sample. But whenever you're in a setting where I have to give you multiple samples on the same input, you're in trouble. Any other questions? Okay, sorry I took up a lot longer than I was supposed to. Yeah, thanks. If you have any questions, please ask me offline.
We have a long lunch break until 1, and then Andre will be speaking at 1 o'clock.